In my previous videos, I have taught you how to install Vivado. I have introduced the concept of a comparator, and I have shown you how to design behavioral VHDL to make that comparator work, reminding you that it came from this truth table and these equations from those K-maps. So we want to test to make sure that this actually works. We do that by creating what is called a test bench. Now, we've shown you how to create design sources before. Let's go ahead and create a simulation source. I'm going to click the Add Sources button. I'm going to select the Create Simulation Source because simulation do not become part of my final design. I hit Next, I hit Create File, and in general, my rule is to call it the design file's name, which is comparator 1b, and then an underscore TB. Vivado does not like spaces in file names, so I use underscores. Make sure that your file type is VHDL. If it reads as Verilog, it is likely that you accidentally created a Verilog project, which will cause you problems since this lecture series is about VHDL. Okay, so I've given it a name, made sure the data type is correct. I hit OK, finish. It will ask if I would like to add ports. In general, I don't add my ports here. I do it in VHDL. However, for test benches, we're not going to add any ports at all, even once I create that design or the simulation file. You will notice there is no file up here in my design sources because it's just a test. But down here, I have a comparator 1-bit test bench. I will double click on that, and you will see this empty design file ready to be used. As I mentioned earlier, we will not be using any ports. So what we need to do is we need to make this design file aware that the comparator 1-bit that I want to test exists. We're going to do this through something called a component declaration. This is declaring that it can use my 1-bit comparator. The easiest way to do this is go to the design file of interest, highlight the entire entity, starting from the entity to the semicolon, hit Control-C for copy, head to the architecture header, that's right here at line 39, and push Control-V, that pastes. I will then rename the word entity to component and change the end statement to end component. This is equivalent to going and getting out of a bin full of comparators. It is an infinite size bin that I can use any number of. I have made them available by putting them on the desk, but they have not been put into my circuit yet. To put them into my circuit, I need to create a component instantiation. So just as a quick reminder, this is the architecture header, this area between the architecture statement and the begin. I need to also note that this is the component declaration. I need to create one of these to test it. So I'm going to create what is called the component instantiation. I do that by first giving it a name. The name in it that I will give it in a test bench is UUT. This stands for unit under test. I will then tell it what I'm testing, that is the comparator 1-bit, and I need to create what is called a port map. This is a description of how the ports are connected. Now, as a matter of organization, I generally like to list all of my ports first. So I say X is going to get mapped to something. That is a mapping arrow is what I call it. I'm sure it has an official name, but I'm going to be lazy and call it my mapping arrow. I'm then going to tab over so that my next line is lined up and say that I need to map Y to something. GI gets mapped to something. LI gets mapped to something. GT gets mapped to something. And LT gets mapped to something. Close parentheses, semicolon, and now I have the rough structure of what I want to implement, but I need to fill in the signals. You will notice something. In my previous design of the comparator 1-bit, I created these ports, X, Y, GI, LI, GT, LT. When I created those ports, the VHDL automatically created signals within them of the same name. I was able to use these signals down here. Signals do not exist on their own. Much like other programming language, I have to declare variables to make use of them. However, here I don't make variables, I make signals. Anytime I make something exist, meaning I make a declaration, it must happen in the architecture header. So I'm going to write the word signal, and I'm then going to give it the name, well, I want XYGI. XYGILIGTLT. I'm missing the LI signal is what I forgot. So LI comma. I will then give them a data type. They are standard logic. Now, this will potentially work. However, I like to be very detailed in my design. And the problem here is that there is no differentiation between my signal X at the test bench level and my signal X that will happen inside of my comparator. Now, strictly speaking, this is not a design problem. It is just a code problem, code readability problem. So what I'm going to do is I'm going to add underscore TB to the names of all of my signals. What this allows me to do is indicate that my signals at my test bench are different than the signals inside of my device. Now I'm going to tell it that those ports X is mapped to the signal XTB. I'm connecting a signal to the port X. Specifically, if I go back here, I'm looking at this. Inside of the box, there's a port called X, Y, GI, and LI. Outside of this, in my test bench, I'm going to have a signal connected to that port called X underscore TB, Y underscore TB, etc. Let me go ahead and fill this out. All of my errors are now gone, and I have successfully port mapped my comparator. So now, the next thing that I need to do is I need to apply stimulus to these signals, meaning I need to set my input values to something and then look at what happens to my outputs. Now, I'm going to change something slightly to make my life better, is I can, in simulation, create what are called initial values. This does not turn into real hardware. This only works in software. Now, the rule is I do not want to assign initial values to my outputs because my circuits are supposed to be telling the outputs what they should be. So I'm going to create a new line for signals that are associated with inputs and a different line for signals that are associated with outputs. So these are my input signals. Noticing that the dash dash is what is called a comment, meaning that it is simply for human reading to understand what is happening. And these are my output signals. To make an initial value, some value for them to start, I write colon equal 0. Apostrophes are how we declare that it is a standard logic type. So apostrophe 0 will make X, Y, LI, and GI test bench signals all start at the value 0. I am not going to tell GT or LT what to start as because those are outputs. Now, starting below my comparator port map, that component instantiation, I'm going to have to create what's called a process to tell the values of those inputs what to be. I could put this process before or after, but I prefer to put it after as a simple matter of organization. So I write the word process, begin, and I always write end process. If I write a begin, I want to write the end because it is too easy to lose track of those ends, and it is a very difficult thing to debug. All right. Control S saves. I push Control S constantly to make sure that I don't accidentally lose any progress. So I recommend saving your devices by pushing, or your designs by pushing Control S. A matter of formatting, I generally tab in for each layer of things that I would like to write in new code. So the process is against the left. I will tab in once to tell it what the process is doing. What that process is doing is assigning values to X, Y, LI, and GTB. So as a matter of the fact that I'm a slow typer, I'm going to do a bit of pasting. I'm not sure that sped anything up. And I'm going to assign values to each of those signals. All right, so I've already started at x is 0 and y is 0. And in fact, I'm going to be what I'll call wrong in this test. I'm going to make this test very simple, but so simple it is incorrect, in that I'm not even going to test my GT and LI inputs at the moment. Never mind, I will. It's so wrong, I was going to try and simplify this, but it's too far wrong to make myself feel okay about this. So we start at zeros. Then I'm going to change these values to, well, maybe x is still 0, but y will be 1. And these are going to stay 0. We use semicolons to mark the end of lines, and now I have set values for each of those. However, I need to let the process know how long to hold those signals, so I'm actually going to start with a wait for 10 nanoseconds. This means the process will start where everything is, all the inputs are zeros. It will wait for 10 nanoseconds and then set the new values. One thing that I will point out is it would be equally correct to delete all of the things that are zeros because they are already zero, so there is no need to change them. However, I'm going to leave this so it is very explicit what my inputs are at each point in time. I'm now going to copy and paste several times. This allows me to step through 0, 0, 0, wait for 10 nanoseconds, 0, 1, 0, 0, wait for 10 nanoseconds, 0, 1, 0, 0. I could step through the entirety of the truth table shown here for all of my inputs and make sure that my outputs match. However, I'm just going to test a subset of this to keep this video not from being too incredibly long. So let's test first the y is greater than x. Let's test the x is greater than y. Let's test the situation where x and y are equal, but the Li is true. And also x and y are equal, but Gi is true. Then I'm going to type the word wait at the end of this. This will stop the process from running over again. If I don't have a wait, it will simply say process, step through all of this, and then start again over and over and over again. That is fine, but it makes it more difficult to read the test bench waveform. Speaking of that test bench waveform, assuming that I have done this all right, I can now hit the Run Simulation button over here in the Flow Navigator. I will always start by pushing this arrow, the 4 arrows pointing outward. This is the Zoom Fit button, which will show you the entire duration of your simulation that did run. If you happen to need to run it longer, you can see up here in the top, there is a play button and then a play button with what looks like a cursive M underneath it. That is, in fact, a T in parentheses, and that button allows you to run for a specific amount of time. In this case, if I were to push it, it would run for an additional 400 nanoseconds. I could change that, timescales or numbers. However, my simulation is done running. You can see it step through each of those combinations and then stop. So I'm going to click on the waveform, which creates a yellow bar. I can then push the magnification zoom button, which will zoom in on the yellow bar. We can see my inputs, X, Y, Li, Gi, and we can make sure that the outputs are doing what they're supposed to based on the inputs. So at this point in time, my inputs are all 0, which means that it is neither less than or greater than, which means I am correct in that GT and LT are both 0. Excellent. Next point in time, I can see that Y is greater than X, so X is less than Y, so the less than is asserted. Next change, Here we have X is greater than Y, so the greater than is a sign. At this point in time, X and Y are equal, but there is a less than input that gets propagated through. Here, the same is true. X and Y are equal, but the greater than input is there, so we propagate it through. It looks as though this works. This is not an exhaustive test, but it is representative. Now that I believe that my comparator, my 1-bit comparator is working, I can prepare to work on the 3-bit comparator. This will be done in my next video.